Every single second of every single day, there's a silent war raging just high above our heads. The sun is constantly blasting a storm of charged particles at our planet, and Earth is fighting back with this invisible shield. But sometimes that shield cracks. So the big question is, how do we actually measure the power of that attack when it's all happening thousands of miles away in the vacuum of space? Okay, let's get into it. Yeah, that's the central mystery we're going to unravel today. For scientists who are trying to forecast dangerous space weather, it's not enough to just know that our shield is getting hit. They need to know how fast it's breaking down. But trying to get that measurement directly, it's next to impossible. It'd be like trying to measure the speed of a hurricane by, standing right in the middle of it. All right, so first things first, let's set the scene. Before we can really dig into the crime, we need to understand the crime scene itself, Earth's absolutely incredible magnetic shield. I want you to think of it like this. Earth is basically a giant bar magnet, and every single second of every single day, there's a silent war raging just high above our heads. The sun is constantly blasting a storm of charged particles at our planet, and Earth is fighting back with this invisible shield. But sometimes that shield cracks. So the big question is, how do we actually measure the power of that attack when it's all happening thousands of miles away in the vacuum of space? Okay, let's get into it. Yeah, that's the central mystery we're going to unravel today. For scientists who are trying to forecast dangerous space weather, it's not enough to just know that our shield is getting hit. They need to know how fast it's breaking down. But trying to get that measurement directly, it's next to impossible. It'd be like trying to measure the speed of a hurricane by, standing right in the middle of it. All right, so first things first, let's set the scene. Before we can really dig into the crime, we need to understand the crime scene itself, Earth's absolutely incredible magnetic shield. I want you to think of it like this. Earth is basically a giant bar magnet, and it creates this massive magnetic bubble all around us. We call it the magnetosphere. This bubble is what deflects the solar wind, this relentless stream of particles that's always blasting out from the sun. Seriously, without it, our atmosphere would just be stripped away. It is our planet's most critical line of defense, bar none. But, and this is a big but, this shield, it's not invincible. Under just the right conditions, the sun's assault can actually create a breach. And that process is right at the heart of our scientific detective story. The culprit has a name. It's called magnetic reconnection. Now, what's so cool is how this works. The solar wind, you see, it carries its own magnetic field. And if that field is aligned just right, basically pointing opposite to Earth's, the two sets of field lines can snap and then explosively reconnect with each other. And just like that, a hole is ripped open in our shield, and all that solar energy in those particles just start pouring into our atmosphere. And look, this isn't just some abstract science thing. During a really strong cosmic storm, this erosion can be so bad that the edge of our magnetic shield, the magnetopause, it gets pushed back inside the orbit of our GPS and communication satellites. That leaves them totally exposed and vulnerable. So you can see why knowing how fast this is happening is, well, it's absolutely crucial. Which, of course, brings us right back to our big problem. Measuring this reconnection rate right where it's happening is just insanely difficult, not to mention dangerous for any spacecraft that tries. So scientists had to become detectives. They had to go looking for clues left behind at the scene of the crime. And you know what? They found those clues. They found them in a very specific funnel-shaped part of our shield. So we're heading to a place known as the cusp. So the cusps are basically these two big funnel-shaped openings in our magnetosphere. One over the North Pole, one over the South. They're the natural front doors for those solar wind particles that sneak through during a reconnection event. This is where all the evidence gets channeled, and it's where our satellites can get a really good look at what's going on. So what is this evidence exactly? Well, let's walk through it. Picture a cosmic racetrack. When that reconnection happens way out in space, a whole flood of charged particles, ions, get flung towards Earth. But here's the key. They don't all have the same energy. The high-energy particles, the really fast ones, they zip down the magnetic field lines and they smack into the atmosphere first at lower latitudes. Meanwhile, the low-energy, kind of slowpokes, they take their sweet time. And by the time they show up, that magnetic field line has actually moved, kind of like a conveyor belt, to a higher latitude. And what you get is just brilliant. A satellite flying through the cusp sees this beautiful telltale signature, a cosmic rainbow of particle energies, right? You've got high energies at one end and low energies at the other. This pattern, it's called an ion dispersion. and it is the unmistakable fingerprint of magnetic reconnection. The slope of this rainbow, how steep it is, that's what holds the secret to the reconnection rate. Okay, so our detectives had the clue, but to prove that they could use it to reliably measure the speed of the breach, they needed a forensics lab, a virtual one. So what they did was they used this incredible supercomputer model called Gamma-Chimp to build a complete digital replica of Earth's magnetosphere. Then they blasted it with a steady, simulated solar wind, and they traced the paths of, get this, 1.7 times billion individual particles. The goal was simple. Could their virtual satellites pick up that same cosmic rainbow signature? And, more importantly, could they accurately decode what it was telling them? And the scientists running the simulation, they put it perfectly themselves. Their whole goal was just to demonstrate, to prove that this remote clue, this cosmic rainbow, could be used to accurately calculate the reconnection rate. This was it. This was the critical test of their entire idea. All right, this is the moment of truth. This is where it all comes together. Inside their simulation, they finally had the power to check their work and hopefully crack the code. Now here's the absolute beauty of a simulation. You control everything. The scientists can measure that reconnection rate in two totally different ways. First, they could measure it directly at the source, the ground truth that they could never get in real life. And second, they can measure it by using their virtual satellite to analyze that ion dispersion clue. The million-dollar question was, would the two numbers match up? First up, the ground truth. Inside the simulation, they could directly measure the electrical field that was created as the magnetic shield was being ripped open. This gave them an average reconnection rate of about 0.65 millivolts per meter. You can just think of that as the speed of the breach. This was their baseline. This was the number to beat. And they matched. The results were just remarkable. Now, don't worry about all the little details on these charts. Just look at the general shapes of the lines. The graph on the left shows that ground truth rate measured directly, and the graph on the right, calculated only from that remote cosmic rainbow clue, shows the exact same pattern of peaks and valleys. It was a near-perfect match. It proved the technique works. The case was cracked. But just like in any good detective story, there was a twist. It turns out the reconnection rate wasn't steady at all. Even though they were hitting the virtual Earth with a perfectly constant solar wind, the rate was fluctuating up and down by about 30% on a roughly 5-minute cycle. So what was causing this? The simulation gave them the answer loud and clear. These fluctuations were being caused by the spontaneous formation of these things called magnetic flux ropes. You can see a visualization of them here. They're these huge, tangled tubes of magnetic fields that form right on the boundary of our shield. The simulation showed that as these ropes form and break apart, they cause the reconnection rate to pulse. It's not a steady leak. It's more like a sputtering, fluctuating breach. So, this is all incredibly cool, but what does cracking this code actually mean for us back here on Earth? Well, it all boils down to one thing: better forecasting. You see, this newly validated technique is a total game changer for new satellite missions. Older satellites, like the DMSP series, they could get a really rough order of magnitude kind of estimate, but upcoming missions like tracers are custom built for this kind of work. They have higher resolution instruments, and they fly in a perfect noontime orbit to repeatedly sample the cusp, which is going to allow for much, much more precise measurements. And when I say repeatedly, I mean it. The Tracer's mission is designed to fly through the cusp over 3,000 times, and each and every pass will use this exact technique to take a snapshot of the reconnection rate, building up a detailed, evolving picture of our shield's health in a way that we've just never been able to do before. Which leaves us with this final, really tantalizing thought. As our technology gets better, and as we get more and more eyes on the cusp, could we one day create a real-time weather map of our magnetosphere? You know, a constant readout of our shield's integrity, giving us that advanced warning we so desperately need to protect our technology and ourselves from the next great cosmic storm.